A bag contains 5 yellow and 4 green marbles. 3 marbles are selected at random from the bag without replacement. Show that the probability that exactly one marble is yellow is 5 by 14. Okay. So if 3 marbles are selected and one is yellow, then we may get yellow as the first marble and green as the second marble and another green as the third marble. Let's find probability of just this. That would be a 5 upon 9 for the first yellow marble. Second marble is green, so 4 upon the denominator will become 8, and another green marble would be 3 upon 7. Okay, now this is when we have yellow, green, green. We can also have green, yellow, green, and green, green, and yellow. So we must multiply this probability with 3, and that should give us the desired answer. It gives 5 by 14 as required. Part B, we do times 3 here. Okay, part B, random variable x is the number of yellow marbles selected. Draw the probability distribution for x. Okay, so we'll write small x here. Probability x is equals to x here. Okay, so we may have zero yellow marble, or one yellow marble, or two yellow marbles, or all three would be yellow marbles. Let's find these probabilities and fill up the table. We already know the probability of one yellow marble. That's this, 5 by 14. Okay, now I'm finding probability of getting 0 yellow marbles. That would be green, green, and green. So 4 upon 9 times 3 upon 8 times 2 upon 7. Which gives 1 upon 25. Okay, next I'm finding this because it's easier to calculate probability that all three marbles are yellow. So yellow, yellow, and yellow would be 5 upon 9, then 4 upon 8, then 3 upon 7, which gives 5 upon 42. All right, so we write 5 by 44 here. Okay. 5 by 42. Okay. Achha. For this last probability, what you can just do is add all the other probabilities and then subtract the result from 1. That is the easiest approach to go by. However, I'm going to show you how you would find this from scratch. Okay, so we have to find the probability that we get 2 yellow marbles. So that would be probability of getting a yellow and then a green, and we will multiply that with 3 because that could also be yellow, green, yellow, or green, yellow, yellow. So probability of getting a yellow marble is 5 by 9. Probability of getting the second yellow marble would be 4 over 8. Then probability of getting a green marble will be 4 by 7. And then we multiply this with 3. Okay, that would give us 10 by 21. Now, you should add all these probabilities and confirm that you're getting a sum of 1. Okay, So part B is also done. We have our probability distribution table. In part C, we have to find the expected value. For this, we have a formula given in the formula sheet as well, which is expected value equals to summation of x times probability. So x is 0, probability is 1 by 21, plus x is 1, probability is 5 by 14, then x is 2, probability is 10 by 21, and then x is 3, and probability is 5 by 42. All of this gives us 5 upon 3. The random variable x takes the value -2, 1, 2, and 3. It is given that probability x equals to x is kx squared, where k is a constant. Draw the probability distribution table for x, giving the probabilities in numerical fractions. Okay, so x in the upper row, probability capital X equals x in the lower row. X could be -2, 1, 2, or 3. All right. Now the probability is k times x squared. That means probability of getting a -2 would be k times -2 squared, which is 4k. Okay, then probability of getting a 1 would be k times 1 squared, which would just be k. And then we'll have another 4 into k for this, and then a 9k for this. Now, sum of all probabilities is 1, so 4k plus k plus 4k plus 9k equals 1. So we get 18k equals 1, which gives us k equals 1 by 18. Okay. Now we can enter all the probabilities. This becomes 4 by 18. This is just 1 by 18. This is 4 by 18. And this is 9 by 18. Okay. Part A is done. Part B, find the expected value and the variance. So we have formulas for that. Expected value is summation x times probability. So -2 times 4 by 18 plus 1 times 1 by 18 plus 2 times 4 by 18 plus 3 times 9 by 18, which gives 2.56. And now we need to find the variance. Formula for variance is summation x squared times p minus expected value squared. So now we will square the x, so -2 squared times probability plus 1 squared times its probability plus 2 squared times its probability plus 3 squared times its probability minus expected value squared, so 2.56 squared. Okay. This gives 3.91. Eric has 3 coins. One of the coins is fair, and the other 2 coins are each biased, so that probability of obtaining a head on any throw is 1 by 4, independently of all other throws. Eric throws all 3 coins at the same time. Events A and B are defined as follows. Okay, so before we read events A and B, let's see what probabilities are we getting for the fair dice and the unfair dice. So if it's a fair dice, then the probability of head is just going to be half, and probability of tail will also be half. So for fair dice, probability of head would be half, and probability of tail will also be half. And for a biased die, probability of head is 1 by 4. That means probability of tail is 3 by 4. Okay. Event A is all three coins show the same result. So either head, head, head or tail, tail, tail. And B is at least one of the biased coin shows a head. Part A, show that probability of B is 7 by 16. Okay, now three coins are thrown and one of them is fair and two of them are biased. Let me make sure the two coins are each biased. Yes, so one of them has to be a fair coin and other two will be biased. Okay, part A says show that the probability of B is 7 by 16 and B is at least one of the biased coins shows a head. So at least one of these two has to be ahead. So we have so many cases. For example, the first one, the fair coin could be head or tail. It doesn't make any difference. Let's say it's head. Then let's say the first bias coin has to be a head. Other one can be a tail. Or it could be a head for the first fair die and then a tail for the first bias die and a head for the second bias die, or tail, head, tail, or tail, tail, head, or even we could have uh, all three heads. So these are a lot of possibilities. In fact, I think I may have missed some. It could also be THH. Yeah. So instead of adding all these six probabilities, there's a better way of doing this is that we do 1 minus probability that none of these biased coins have a head. So 1 minus probability, none of the two biased dice shows a head. So 1 minus, now what cases do we have? We have probability, none of the two biased dice shows a head. So the first fair dice could still show a head. So head and then tail and tail. This is the fair dice and these two are biased. And plus probability, the first one is also a tail, the fair dice also shows a tail, and the other two shows head. Sorry, they have to be tail as well because they can't be a head. Okay. Now we'll do 1 minus probability of getting a head in a fair dice is half. Probability of getting a tail in a fair dice is 3 by 4. Then plus half, same thing, 3 by 4 into 3 by 4. Enter this in the calculator, you will get 7 by 16, and that is what we had to show. Part B, find probability A given B. Okay, A is all three coins have the same result, and B is at least one of the biased coins shows a head. Okay, so if this has happened, at least one of the biased coins shows a head, then A also has to be head, head, and head. So for part B, it says probability A given B. So numerator is probability A and B, and denominator is probability of B. Probability of B we've already found, it's 7 by 16. Probability of A given B would mean this is also happening and this is also happening simultaneously. So if this says that all the coins show, all the three coins show the same result and this says at least one of the biased coins has to be ahead, then all three of them have to be head, head, and head. So head for the fair coin, head for the first bias coin, head for the second bias coin. Okay, so this would give us half times uh, head for the first bias coin, half 1 by 4, another 1 by 4, divided by 7 by 16, which gives us 1 over 40. Next is the random variable x is the number of heads obtained when Eric throws the three coins. Draw the probability distribution table for x. Okay, let's do that here. Okay, so number of heads could be, this would be probability x equals x, either 0 heads or 1 head or 2 heads or all 3 heads. Okay, so probability of a 0 head would mean tail and tail and a tail. Tail for the fair coin, tail on the biased coin, tail on a biased coin. So that would be half times tail for the first biased coin is 3 by 4 and again 3 by 4. This gives 9 by 32, which I'm entering here. Okay. Next is that we get 1 head. 1 head would mean either head here in the first one, in the fair one, and then tails in the other two. Tails for the bias coin, or a tail here and then a head and a tail. So the fair coin is a tail, then the biased coin is a head, and then the other biased coin is also a tail. Or we could have tail for the first biased coin, a tail for the second biased coin, a tail for the first fair coin, and then a tail for the biased coin, and then a head for the biased coin. Okay, so we'll have to add all of these cases together. We have a half here, then tail on the biased coin is 3 by 4, again 3 by 4, then plus, okay, then we have half for the tail on a fair coin, then head on a biased coin is 1 by 4, and tail on a biased coin is 3 by 4. Similarly, plus tail on a fair coin is half, tail on a biased coin is 3 by 4, and head on a biased coin is 1 by 4. These are actually equal. We could have just doubled this and gotten the same answer. Okay, this gives 15 by 32. Okay. Next, we have to find the probability of getting 2 heads and then probability of 3 heads. What I'll do, I'll directly find for 3 heads because that's a lot easier. Head on the fair one, head on the bias one, head on the bias one. So half times 1 by 4 times 1 by 4, which is 1 over 32. So I'm writing 1 over 32. And this one we can find by subtracting the sum of the other 3 from 1. which gives 7 over 32. So we write 7 upon 32 here.